Math, it's all about math, the wonderful world of math. Welcome to the wonderful world of math. Howdy ho, neighborinex. This time we're going to talk about symmetry in polar coordinates. Specifically, we want to talk about the reflection symmetries, symmetry about the x-axis, or in polar coordinates, about the line, theta equals 0. Or, if you're feeling like it, theta equals pi, same line. Symmetry about the y-axis, or as it's known in polar coordinates, theta equals pi over 2, or theta equals 3 pi over 2. And symmetry about the origin, now in polar coordinates known as the pole. Symmetry about the pole. You could also talk about rotational symmetries in polar coordinates, which aren't nearly as bad as they would be in rectangular coordinates. In fact, it's really pretty easy, but we want to focus right now on these three symmetries, the kinds we are familiar with from rectangular coordinates. So let's talk about symmetry about the line theta equals 0. Now, if we've got a point here, it has polar coordinates r comma theta. Symmetry about the x-axis, right, means that I'm going to have a point on the other side of the x-axis. It means that this distance, the distance from the x-axis, will be exactly the same, but in the opposite direction. So you're going to end up with a point down here now. And we need to be able to describe this term, this point, in terms of its relation to r comma theta. So let's think about this again. If this angle is theta, what is this angle? This is not theta, it is the opposite of theta. It's the same amount of radians, but in the opposite direction. R is the same distance from the origin for both of these. So anytime you have a point r comma theta on your graph, and you also have a point r comma negative theta, then that means you're going to be symmetric about the polar axis, or theta equals 0. So how does this work? Let's say we have an example, an equation r equals cosine theta. I know that r comma theta is a solution. If I plug in r for r and theta for theta, then this is true. Okay, great. So if I plug in r for r and replace theta with negative theta, is it still true? When we do this, we're going to use algebra and trig identities to simplify after plugging in. So cosine of negative theta, using the cosine even identity, which says that for all x, cosine of x is equal to cosine of the opposite of x, it means that cosine of negative theta is in fact equal to cosine of regular theta. So if this is true, then this is also true. So yeah, this one must be symmetric about the x-axis. Now the next one we'll do is a little bit different order than when we do it in rectangular coordinates. It's easier to do next symmetry about the pole. So now imagine we have a point, and just for the sake of making it different, let's put it over here in the second quadrant. We have a point, and it's going to be called r comma theta. It's some distance r from the pole, and it's rotated theta radians from the polar axis, right? Or the positive x-axis. This is what we've got so far. Now we want something that's symmetric about the pole, so we want somebody that's going to be over here, the same distance in the exact opposite direction. So how do we tell an angle is a complete turnaround from the way it used to be? In fact, we have an expression for it, doing a 180, right? We need our point to do a 180, essentially. In other words, to go from here to here, it's making a straight line, and that this is going to be pi. So if we take theta and pi together, we'll get this angle. This angle altogether will be theta plus pi, and we'll have the point r comma theta plus pi, or pi plus theta if you're feeling like that. So now we have a test for symmetry about the pole. If you can replace r comma theta with r comma theta plus pi and your equation is still true, then you are symmetric about the pole. So let's try now symmetry about theta equals pi halves, symmetry about the old y-axis. Let's suppose that we have a point somewhere, and we're going to call it r comma theta. And we want to find another point that is on the opposite side of the y-axis. So from here, you go this way, and then you go this way the same amount in the opposite direction from the y-axis, and you get a new point here. How would we describe this point? If we have an angle theta, right, how do I describe the angle here made in relation to the original angle? This one can be kind of tricky, so we're going to do this case by case. Apparently, this one right now is in the third quadrant, and for ease, we'll assume that it's between 0 and 2 pi, because if it's not, you can find somebody coterminal. That one doesn't make a difference. Your trig functions are periodic. But if this angle is in the third quadrant, what we notice is that this guy and this guy have the same reference angle, right? So how do you describe the reference angle for somebody in the third quadrant? We said that for somebody in the third quadrant, the reference angle, alpha, that's going to be the positive angle, that means counterclockwise, between the nearest x-axis, in this case the negative x-axis, and the terminal side of your angle. So this would be the reference angle for this dude. Now, the other guy over here that we want is going to be this angle, right? Or you could think of it as this angle. Either one will do, but we'll stick with the shorter one for now. This guy has the same reference angle. Now that's got to be counterclockwise. So what we see about the difference between the green and the purple arrow is that they're opposites. So that's the two equations that will allow us to say a relationship between the angle we were given and the angle for this guy. Now, if beta equals negative alpha, that means that negative beta equals regular alpha, and we can do substitution. This allows us then to solve for beta. Add beta to both sides, subtract theta from both sides, and we get that this angle here is going to be pi minus theta. The trick for us is showing that this equation is actually not dependent on our starting in the third quadrant. That if we start in the second quadrant, the relationship between reference angle and actual angle will be the same. Or if we start in the first, or if we start in the fourth. Cool, right? We'll do one more, and I will then encourage you to show that this is true for the other two quadrants. Suppose now we have a point, r comma theta, in the first quadrant. Our goal is to have a point over here reflected across the y-axis, or the vertical line theta equals pi halves. Now, if this is theta, we want an angle over here, which we'll continue to call beta. In this case, the reference angle is just equal to alpha, so that this angle, alpha, is the same reference angle. And the formula for reference angle in the second quadrant is pretty easy. This one plus this one adds up to 180 degrees, or pi, a straight line. So pi equals alpha plus beta. But we also know that alpha was just straight up equal to theta if theta was in the first quadrant. So solve for beta by subtracting pi from both sides. And so this angle is pi minus theta. This point is r comma pi minus theta. Just like here, this point turned out to be r comma pi minus theta. So now I'd like you to try to show that if we start out with a point in the second quadrant, that this is going to be r comma pi minus theta by using the reference angles just as we did in the first example and the second example, right? But this time, I'm going to let you check your work. I'm going to do it after you do it. So try it, pause me, and bring us back. All right, back in 5, 4, 3, 2, 1. Now this angle is theta, and the reference angle is alpha. And this angle is the same reference angle, right? So this angle, which we don't yet know is pi minus theta, which we've been calling beta, right, is actually the same, exact same as its reference angle this time. It's just positive x-axis, because it's the closest x-axis, counterclockwise in the positive direction to the terminal side of this line segment here. So the important thing is that theta plus the reference angle, alpha, adds up to pi, because theta's in the second quadrant, that's how that works. And then you replace alpha with beta because they're equal. And then you solve for beta, and beta is going to be equal to pi minus theta. I leave it for you to show that if we start out with a point in the fourth quadrant, that the point that is symmetric about theta equals pi over 2 has coordinates r comma pi minus theta using the same approach. So let's do a full-on example. Find any reflection symmetries of r equals 3 plus 2 cosine theta. We're not just going to check to see if this is symmetric about theta equals 0, or theta equals pi halves, or the origin. We're going to check all three. We'll show one that works and some that don't work. If it's symmetric about the old x-axis, the test we devised was theta, r comma theta implies r comma negative theta. That if we plug in r for r and negative theta for theta, is it still true? So we plug in r for r, and we're going to plug in negative theta for theta. Last time we did this, we were able to use the cosine even identity to say that this cosine of negative theta is actually equal to cosine of regular theta, which is exactly the original equation now. So yeah, this one checks out. Hooray! So now let's check to see if it's symmetric about the pole. We're going to plug in r for r and theta plus pi for theta. Now the cosine even identity isn't going to do you any good here. What we need is the cosine sum angle identity, which says this. Notice that this says minus even though this says plus. So we've got r equals 3 plus 2 times, and this is now parentheses, because this one term is going to go into two terms using this identity. So cosine of the first angle times cosine of the second angle minus sine of the first times sine of the second angle. That is the cosine sum angle identity. Now the next thing we want to do is we want to simplify this. We know that cosine of pi and sine of pi are things that we can evaluate fairly easily. Sine of pi, in fact, is 0. So this just goes away. Cosine of pi is negative 1. And this turns into r equals 3 minus 2 cosine theta. This is not true. So we know we're symmetric about theta equals 0, and we definitely do not know that we are symmetric about the pole. What about symmetric about the old y-axis? We said that if r comma theta was a solution to the equation, then we might also have r comma pi minus theta. That was the test we devised, so we plug in r for r, and we plug in for theta pi minus theta. Pi minus theta. And this time we're going to use the cosine difference angle identity. Very similar, but now both signs are opposites. So now r equals 3 plus 2 times, again, parentheses, because this is going to split into two terms, cosine of the first angle, that's cosine of pi, times cosine of the second angle. Now this says plus cosine sine of the first angle times sine of the second angle. This is what we get when we use the cosine difference angle identity. And like last time, we're going to simplify each of these. Like last time, this one is 0. Cosine of pi is again negative 1. So we get this. And this is not equal to the original equation. 3 minus 2 cosine theta, still not equal to 3 plus 2 cosine theta. So this is not true. So why are these reflection symmetries useful? If I'm graphing r equals 3 plus 2 cosine theta for the first time, and I am making a table, if I know that it's symmetric about the x-axis, the line theta equals 0, then I know that whatever r values I get from theta in the first quadrant, I will also get for thetas in the fourth quadrant on the opposite side, right? If whatever I get for theta in the second quadrant, I will also get the same r values for theta in the third quadrant. So you get to do half as much work if you know it's symmetric about the x-axis. You plug in theta values for the first two quadrants, and then you automatically get to copy-paste r values for the third and fourth quadrants. You might also notice that there wasn't anything special about 3 or 2. I could just as easily have done this whole process for anything in the Limassol family that said a plus or minus b cosine theta. You'll get the same answers for each of these symmetry tests. So let's try the other family of Limassol, the sine family, a plus or minus b sine theta. So let's try substituting r for r and negative theta for theta in this more generic equation. Now sine doesn't have the cosine even identity. It's not cosine, it's not even. In fact, it has the sine odd identity that says sine of negative x is the same as negative sine of x. So that if I take the opposite of x, that's the same as taking the opposite of sine of regular x instead. In other words, you can basically factor this negative out in front. Now when I multiply plus or minus b times negative 1, I'm going to get minus or plus b. So maybe you're not used to working with plus and minus versus minus plus, but let's break this down then. This means two things. It means you either started with this or you started with this. One of those two equations will be your original equation. Now, based on that, you do this substitution, and this minus or plus notation means that after simplifying, knowing that r comma theta is a solution, we're looking to see now if a minus b sine theta is a solution. So that this top one corresponds with this top one, and they don't match. So that's a no. Over here, on the other side, we've plugged in r for r and negative theta for theta, and we followed this one. We got the bottom one here. So that's going to be r equals a plus b sine theta. And they don't match. So this is also no good. So that's how we read this minus or plus notation. It just means that the top stays with the top after simplifying. So let's now see if this thing is symmetric about the pole. We're going to test to see if whenever r comma theta is a solution, is r comma theta plus pi also a solution. So we'll plug in r for r and theta plus pi in place of theta. Now here we're going to use the sine sum angle identity. Notable feature of the sine sum angle identity, plus, also plus. So we'll have r equals a plus or minus b times parentheses, again, because this one term is going to split into two, like this. Sine of the first angle times cosine of the second, plus sine of the second times cosine of the first. And we're going to simplify this, and this will simplify. So this guy goes away, multiplying by 0, right? And when I multiply sine theta times negative 1 and simplify that, I'm going to end up with the same thing I got last time, actually. A minus plus b sine theta. So this is not equal to what we started with. Not symmetric about the pole. So let's try symmetric about the old y-axis. Is this going to work? And this time the answer is yes, this should work. When we take r and replace it with r, and we take theta and replace it with pi minus theta, we should get the sine difference angle identity this time. The only difference really between the sine sum angle and the difference angle, just like the cosine sum and difference angles identities, was the sine in the middle. So you're going to get the sine of the first one times cosine of the second one minus, this time, sine of the second one times cosine of the first. And then we're going to simplify, right? And just like last time, you have sine of pi equals 0. So that whole term goes away. Now this minus is still there, right? But cosine of pi is negative 1. So I've got a negative in the back and a negative in the front, and they end up just taking care of each other. And this is equal to what we started with. Alright! So anything in this family of limaçons, a plus or minus b sine theta equals r, is going to be symmetric about the y-axis. So it's about time I let you in on a little secret. We had 3 tests for symmetry so far, but you may recall there's more than one way to write a point in polar coordinates. This is both good and frustrating. It means that there's not just one way to express this point in relation to this point. We said that we wanted to think about it as changing the angle, but we also know that taking this point and going in the complete opposite direction can be expressed another way with polar coordinates. rather than changing the angle at all, suppose I rotate theta radians, and instead of going r units this way, I went r units backwards, we have an expression for that. I could also see if whenever r comma theta is a point on the graph, is negative r comma theta a point on the graph. Either of these will allow me to test for symmetry about the pole. In some cases, and this is the really frustrating part, like I promised, this one won't work, but this will. That is frustrating. So that doesn't just mean that one test for symmetry is enough. Sometimes you have to try more than one. Even better, each of these three types of symmetry has a different version where you have a negative r. In each of these three original tests, we came up with a way to do the symmetry with the same r. And this time, we're going to try to do it with negative r. So let's look at this guy. We're going to do a two-step process. Symmetry about the y-axis means this point isn't the exact opposite direction of this point, but it is the exact opposite direction of this point. And this point over here, well, that's if this was theta, then this is negative theta, right? So this point would be r comma negative theta, and this is in the opposite direction from that guy. So if we take the angle negative theta, and instead of going forward r, we go backwards r, we will land here. So negative r negative theta is another way to test for symmetry about the y-axis. And this one here is the toughest one to do with negative r, but we've already done all the hard work. This guy isn't in the opposite direction from this one. It's not. But it is in the opposite direction from this guy here. And I can express this one as having r comma pi minus theta, as we've done in the past. So this point is in the opposite direction from this point. So that if negative r comma pi minus theta is also on the graph whenever r comma theta is, then this should be symmetric about the x-axis. So now we have two ways to test for each of the symmetries, and one of them with a positive r and one of them with a negative r. So now when I'm asked to find symmetries of r squared equals 4 sine 2 theta, a lemniscate, now I can test whichever of these two tests is easier, and if it works, then I don't need to do any more tests. Now in this case, the original test is easiest. I don't want to have to do this sum difference angle identity if I don't have to. Replacing r with r and theta with negative theta, you get 2 times negative theta just becomes negative 2 theta. And this sign odd identity still holds, so this is r squared equals negative 4 sine 2 theta. That's not great. That's not equal to what we started with. You can try this one. It won't work. For symmetry about the pole, we're going to test one of these two conditions. Now, I'm going to pick this one. Instead of squaring r, I'm squaring negative r. And then the other side is 4 sine 2 theta. Theta got replaced with theta this time. And because this is negative r times negative r, we get r squared equals 4 sine 2 theta, which is our original equation. I didn't have to do this sum difference angle identity stuff because this one worked. This is symmetric about the pole. To test for symmetry about the old y-axis, we're going to try one of these tests. So replacing r with negative r and replacing theta with negative theta gives us this. Now we saw what happened when we replaced theta with negative theta before. We didn't super like the results, right? Negative r squared just turned into r squared. And having simplified the stuff on the right hand before, we know that this is going to be 4 sine 2 theta with a negative all the way in front now, which is not equal to r squared. R squared was equal to positive 4 sine 2 theta, and this is not it. Now you can try testing this one. It's going to give you the same information, that it's not symmetric about theta equals pi over 2. So here's the really bonkers thing. Let's take the equation r equals 4 minus 2 sine theta, and we've shown that everything in this family of curves, r equals a plus or minus b sine theta, is symmetric about theta equals 2. But if I use this new test, we'll see that negative r equals 4 minus 2 sine negative theta becomes negative r equals 4 plus 2 sine theta, which is r equals negative 4 minus 2 sine theta. So now check this out. This is the same as the original. This is the same, minus 2 sine theta, minus 2 sine theta, but negative 4 is not equal to 4. This is a problem. So if you use one of these tests and it doesn't work, maybe there's a different test that does work. If you use the test and it does work, you are symmetric about that thing. In other words, a negative result on a test for symmetry in polar coordinates is less conclusive than you're used to. Positive result, still conclusive. Negative result, not conclusive. The last thing we wanted to say here is that if you have one type of symmetry, that doesn't preclude you from having others. Here are two examples of graphs that have more than one kind of symmetry. The cosine 2 theta equals r squared lemniscate actually has all three kinds of symmetry. And the four-leaved rows here, r equals 4 cosine 2 theta, also has all three kinds of symmetry. So while the r squared equals sine 2 theta lemniscate has only symmetry about the pole, this one has all three, and that can actually cut down more work. We knew that if something was symmetric about the x-axis, we only had to do 2 quadrants worth of r comma theta tables, right, to figure out what to graph. But if you've got more than one symmetry, then you only have to do 1 quadrant. That's pretty handy. So here's our summary tests for symmetry. We've got 2 tests for each kind of symmetry, and our dinosaur for the day is Orodromius, the mountain runner. Whoosh! This has been a Badger Bear production of the wonderful world of math. Adios, neighbor Renex.